displaying the screen. I hope my screen is visible.
Yes,
Yes,
sir,
sir,
it
it's
is
Yes,
visible.
visible.
sir.
Yeah,
Yes,
okay,
sir.
great.
Yes.
Uh,
Yes, sir.
so let me just summarize on what we have been doing. I will give you a concept quickly, but then I will solve the numerical, which basically I mentioned that I would rather emphasize for my extra classes. So, okay, we discussed about the linear operators. Remember, the reason for coming up with the linear operators is to have a physical measurement in quantum mechanics. We then did the matrix representation of the linear operator in a basis. We said that then we went to this change of basis and the similarity transformation to see that we can actually represent the same linear operator by different matrices which are related with each other through similarity transformation. Change of basis matrix in that context becomes very useful. Then of course I discussed about the diagonalization, that there exist eigenbasis and the eigenvalue problem, and we have certain advantages of working with it. I will continue to make some more statements on that. And then in the last class I was discussing about this linear operator on inner product space, where I defined an adjoint operator or operation I have written here, where the definition of the adjoint operator was simply that on the inner product space, it can be represented like this. And the reason for choosing the word adjoint, because if we go to the orthonormal basis, then the way the matrix representation of this operator would be nothing but the transpose and the complex conjugate of the one which we were having the original one, the T. So that's the reason why we use this word called adjoint. Remember, the word adjoint we also use for the dual space, the way Dirac tried to explain it, and the same for this bracket. I mean, everything which we are writing on the left hand side of the argument, I mean, let me just show here, on the left hand side could be taken as the adjoint space in the Dirac's notation. And I'm pretty sure that you are now regularly using this kind of notation in your quantum mechanics class, which is the bracket notation. Okay, so one thing which I wanted to make before, a concept which I just wanted to highlight before going ahead with the example. Okay, so what is this concept which I want to take? This is the concept of self-adjoint linear operator, sometimes written SALO or self-adjoint operator, or people call it Hermitian operator, or in real space the same thing is called as symmetric operator. So many names for a single one. And what is that? People are waiting in the, oh god, oh, I haven't changed the, yeah, this is my bad, I haven't changed the way the meeting options for this one. Anyway, so let's just define the self-adjoint linear operator. It is rather simple. It says the way you define the Hermitian matrix. And how do you define that Hermitian matrix? That the adjoint is same as this one. So in principle, in terms of the definition, what does the definition tells us? Then the definition says this. So we talk of a special class of these adjoint operators which are called the self-adjoint operators, and that is the reason the SA. Now these self-adjoint operators we'll see will become very useful in the description of the quantum mechanics, but this operator is same, I mean, whether we call it self-adjoint operator or Hermitian operators at times, or the symmetric operators in the real product spaces. Basically, they mean to say whether we apply this operation on V vector or whether we apply on the U vector and take the inner product, it is one and the same thing. This is what it means. Now, the definition is simple, but the consequences are remarkable. One, it has consequences on eigenvalues. So eigenvalues of self-adjoint linear operator, they are always real. Now, of course, we'll have to show that. So in order to show that, let's just take the eigenbasis. So let's just take the eigenbasis of a linear operator T such that it is a self-adjoint linear operator. So since it's an eigenbasis, so I can write down, of course, for any of those eigenvector, T phi is equal to lambda phi. This is what we wrote in our previous class. Yeah. Now, since we are talking about the self-adjoint operator, so the definition in terms of choosing this, using the same vector on the both sides. So either u or v, I mean anything. So in this case, the eigenvector. So this will of course be true, right? So now since phi is an eigenvector of this linear operator, so you can replace your t acting on phi by, how can you replace that?
Lambda phi.
So lambda phi on left hand side and phi on right hand side. Just look at the previous one. So T phi I replace by lambda phi, it is the eigenvalue equation. T phi on the left hand side. So this is what I have done. And now using the properties of the inner product space, what can I write down for the first one, left hand side?
Lambda star.
Lambda star phi.
Or phi comma phi is equal to lambda phi comma phi,
Lambda
or
phi.
I can write down this equal to. So what should I write? 0 as a number or 0 as a vector?
As a number.
As a number.
As a number. Very good. So what happens now? I have this phi, which are nothing but the non-zero eigenvectors of this Hermitian operator, and I have this. So this guy phi comma phi norm phi cannot be 0, right? This is again by definition. So what will be the consequence? Lambda star is same as lambda. That is the eigenvalue complex conjugate of that is same as this one. But what does this mean? That
Hermitian real values.
lambda is real. So eigenvalues of the self-adjoint or Hermitian operators, they are real. Why it is so important? It is so important because you know that in quantum mechanics, whenever I am making an observation on a state, so let me just write down observation on a state. I am saying that one of my linear operator is acting on one of my state. So it is something like this. Now, if it is an observable, that means that I am going to observe something out of it. And that observations are generally in terms of the numbers. Now, if it is a real observable, physical observable, corresponding result should be a real number and not a complex number which we cannot see. So if you are going to measure spin, you are going to see the value. What is the value of this spin angular momentum? Yeah. So this kind of operator which has the real values, if I write down this kind of equation, see the importance that this eigenvalue is always going to be real, which means that we are going to get the result of some physical observation on the state of the system. So all the physical linear operators which we are going to observe in quantum mechanics, they will be self-adjoint linear operators or Hermitian linear operators. And that's why the physical observables are replaced by these Hermitian. What's the importance of that? So this is one importance. Now there is another importance also. And this importance comes in terms of eigenvectors
Eigenvector.
of non-degenerate or corresponding to distinct eigenvalues are Hermitian operator.
Orthogonal.
Eigenvectors are
Orthogonal.
orthogonal. So let's just do that also in order to see quickly. So how to do that? So let's just see. T acting on phi 1 gives us lambda 1 phi 1. So since we are in this eigenbasis, and T acting on phi 2 gives us lambda 2 phi 2. So a quick proof where lambda 1 is not equal to lambda 2. So let's just do something very quickly the same way we did the last one. So phi 1 comma T phi 2. This by definition of the self-adjoint operator will be equal to T acting on phi 1 comma phi 2. Right? Then just put this
Yes, sir.
eigenvalue equation here. So in this case, it will be phi 1 lambda phi 2, and this one will be lambda phi 1 comma phi 2. Use the inner product space principles. So lambda times phi 1 comma phi 2 is equal to lambda star phi
Lambda
1
star.
comma phi 2. But then, okay, so I should be missing something. Lambda 2 which goes here and lambda 1 which goes here. So I should be having lambda 2 and lambda 1. But these eigenvalues are always real. So I should just write down this as lambda 1 phi 1 phi 2. Remember the first result, the eigenvalues can only be real. So lambda 2 minus lambda 1, taking everything on the left hand side, phi 1 comma phi 2 is equal to 0. Which means what? Lambda 1 and lambda 2 are not same, which is for the distinct eigenvalues. So what will happen, the consequence on phi 1 and phi 2?
They are orthogonal.
Orthogonal.
So this means this one has to be 0, which is the condition of orthogonality. So eigenvectors of the non-degenerate system, that corresponds to the orthogonal eigenvectors, nothing else. Now this makes another interesting remark. What would be the remark? Remark would be that if I have an eigenbasis of a self-adjoint operator, then not only that the eigenvalues are real, but all the eigenvectors are also orthogonal. Orthogonal vectors by definition are linearly independent, right?
Yes,
Yes,
sir.
sir.
So what would be the
Yes, sir.
consequence? The consequence would be that the eigenvectors of the self-adjoint operator, they form
Bases.
Basis.
so eigenvectors of self-adjoint operators form basis. And what kind of basis? Actually, it is orthogonal basis. Now, this is strictly true for non-degenerate ones. So my idea is to first do some problems. I will show you some interesting things. And in fact, you already know it. I am just going to correlate it. And then I will see what happens if I have a degenerate system. Can I still make the same claim? Will the eigenvectors of a self-adjoint operator, but in the case this degenerate system, so there may be certain vectors which will have same eigenvalue, will that also form the basis? So any guesses for that? Any guesses?
No, sir.
It will not form.
No, sir.
So
It
we'll
will not
see.
form.
Okay, we will see that. So, but let's, as I promised, let's have a question on it, and not on that particular topic right now, but let's just go one by one. So let me just give you an example of what we are doing. Now, consider a set phi 1, phi 2, which is a basis. So what kind of we are talking about? V2F space. Fine. And there exists a linear operator T such that, and okay, for the sake of convenience, let's just consider orthonormal set, such that the operation of T on phi 1 that results in I times phi 2 and operation of T on phi 2. So that gives us minus I times phi 1. So what happens that we have a linear operator. If of course I know the application of this linear operator on the basis vectors, then I know the application of linear vector on any of the generic vector, right? So this is the kind of operator which is given to us. So question number 1, give me the matrix representation, and 2, is it a self-adjoint operator? So let me write down matrix representation and whether it is a self-adjoint or Hermitian operator. So how are we going to do the matrix one?
So we can take 1, 0 and 0, 1. Yes.
Yeah. So give me the result. So T1, sorry, no, Y1S, it is just S, which is an orthonormal basis. So what will be this? So this guy and this guy. First column. T acting on phi 1 gives you I times phi 2.
Sir, first column is 0 and iota.
0 and
Yes,
iota.
0 and iota.
What about the second one?
That would
Minus
be minus
iota.
iota.
Minus I 0.
How did you get it?
By operating this on phi 1 and phi 2, what we get is those equations. What those equations satisfy.
So you just used something rather simple, that this is first element you can find out, then of course you can find out rest of the elements in the same way. Since the first row that becomes as a column, so it goes 0 and I, since there was no term of phi 1, there was only term of phi 2, so which goes as I, so on and so forth. So you have an orthonormal basis, matrix representation rather simple. Now is it a self-adjoint?
Yes, sir.
Yes, sir. It is.
Yes.
So you take, let's just do something like transpose and conjugate, and this results in 0I minus I0, which is just the transpose, and then taking the complex conjugate, this becomes minus, this becomes plus, which is basically what the original matrix is, same as, and hence you say yes, that this is a self-adjoint linear, oh, not this, self-adjoint linear operator. Now, third thing, find eigenvalues and normalized eigenvectors. Okay, I will use the word. So what are we going to do next? Eigenvalues, and remember the characteristic equation which we are supposed to solve for this, which is determinant of this guy is 0. That means we are supposed to solve minus lambda minus I, determinant is equal to 0. So can you quickly do that?
So plus minus 1.
So this is lambda square, then plus I square is equal to 0. Or lambda square minus 1 is equal to 0. Just like you said, lambda will be plus minus 1. Is it a degenerate system or a non-degenerate system?
So non-degenerate.
Non-degenerate.
Since the eigenvalues are
Non-degenerate
different,
system.
there is no eigenvalue which is same, right? So it's a non-degenerate one. So let's just try to find out the eigenvectors and then find the normalized one. So lambda is equal to plus 1. So I can write minus minus I, and then it's a general way of finding out. I'm not. This is you use, or I mean you just use the eigenvalue equation directly, whatever. So you must be able to find out some relation. So what relation you find out? Between x and y?
Sir, y is independent coordinate, so we can take it as 1.
But what is the relation which you have found out?
I is equal to I
X is equal to minus IY.
Which is y is equal to ix. I mean it is one and the same
Yes,
thing.
yes.
So now, so if I write this, so if I write x, then I write ix, right? So this is, let's say, the first eigenvector which I am trying to find out. But is this normalized?
No, sir. No, sir.
So how to
No, sir.
normalize it?
No, sir.
Take the norm.
By the norm of the,
By
divide
the-
by the norm of this.
Okay, divide by the norm, figure out what will be your. So I should not write phi 1 because I have already used phi 1 there. So maybe used chi 1 here. And since I used normalized like this, so let me just. So what will be E1 divided by norm? Which will be chi 1 divided by chi 1. Okay.
1 by root 2, 1 iota.
1 over root 2, 1 iota. Okay. Can anybody else confirm it?
Yes,
Yes,
sir.
sir.
Correct.
Yeah.
Yes,
So
sir.
Yes, sir.
normalize it, then of course you do not have your x arbitrary any longer. You have of course this E1 which is represented by 1 over root 2 1 I. Is this a unique one or it is still not a unique one in terms of the vector? Can any other vector also represent exactly the same thing? See, by normalizing you got rid of x's. So it's no longer arbitrary. You have 1 and I is the two numbers
Yes,
here.
sir. It's unique.
So unique.
Except for the fact that I can still multiply it by a phase factor, remember, right? I mean, this is what you have done. So I should replace this so that you do not get confused. Except for the fact that you can still multiply it by a phase factor, and the results of everything, whichever you are going to do with respect to the norms or the inner products, will still remain true or same for evens. This vector remains unique. 1 over root 2, 1 over I. That is one good thing about doing the normalization. Okay, so do the same thing for lambda is equal to minus 1 and give the result.
One by root 2 iota 1.
1 over root 2.
Yes, sir.
Iota 1.
Yeah, you can write down. Oh yeah, this is another thing about this one. Or I could have written 1 and minus iota. It has nothing to do with anything else except that I am using x is equal to 1 and this is this. So this is also another thing which you can see, by the way. I mean, if you go to the previous also, you will see that. So I used y is equal to ix, right? So I put x as 1 and y as iota. I could have equivalently put y as 1 and x as minus iota, and it will still be the result. Yeah. So up to that portion, how these guys are coming up? These guys are coming up by e I raised to power pi by 2, and these are all equivalent eigenvectors. You got the point? Yes, no?
Sir, could you repeat that? I didn't
Yeah.
understand.
See, yeah, of course. So I used y is equal to ix, right? And I wrote x ix. But I could have written this guy as x and minus sorry, y and minus iy also, and it would have been absolutely fine, right?
Yes, sir.
Which means
Yes,
when
sir.
you would have normalized this, what you would have got on normalization?
1 by
1 over root 2
minus iota.
minus iota
minus
and 1,
I1.
right? And you would have said that this guy is still same as the one which we have got, right?
Yes, sir.
Yes, sir.
Yeah, why? Because they are all related with each other by some phase factors. They are all equivalent within those phase factors. You got the point?
Yes, sir.
Yes, sir.
So by
Yes,
multiplying
sir.
it by a given some phase factor which has magnitude equal to 1, you can reach to any of the combinations which you are building. But they are all same because within the phase factor they are all representing the same vector. So this is what I meant. You got this?
Sir, but why the dependency of the second eigenvalue on the we took x and y, we took y equal to ix there. So why is the
Yes.
second
How does it
eigenvalue
matter? No,
dependent
I
on
didn't take
what
y
vector?
as 1 or y minus I. I took a vector and then I normalized it. Nothing else. Since the relation which you were using, see, only relation which you were using is this. I mean, in this case, second, the relation is this, right? This relation could have given you this one or that one. They are all same, right? No?
Right, say yes, sir, I got it.
Okay.
If I took this relation, I got one vector and another one for that. But if I took the other one, then I'll get the second vector as this one, and it will be interchanged.
Right. But why it is that both are the valid solutions? Because they are related with each other just by a phase factor and nothing else. This is what I am trying to emphasize. That within the phase factors, you are getting the results which will still be a valid result. So even when you normalize a vector, then also there is this portion of multiplying it by a phase factor and it is still going to give you the same result. Because remember, all our results will be of the form psi star psi and not only on psi. This is what we discussed to begin with, that the phase factors, absolute phase factors don't affect us. It's only the relative phase factors which affect. But anyway, let me just continue the way you went ahead with. We got E1. This is how we wrote. Okay, 1i and E2. You can use any one and then you will see that the result will still be same. Now, are these two orthogonal, by the way, E1 and E2?
Yes, sir.
You know it or you have checked it?
So we know it.
You know it. Yeah, I mean, because it is nothing but the eigenvectors of the Hermitian operator.
Yes.
Eigenvectors of the Hermitian operators, if they correspond to non-degenerate values, they of course are orthogonal. And in this case of lambda is equal to +1 for one and lambda is equal to -1 for another. Now I am going to do something now interesting. I am going to do something what we call as diagonalization. In this case of operator, self-adjoint linear operator. I mean the one which we started with. So let's just do that. And what I am claiming that I am going to make a matrix out of these eigenvectors. Remember, this is one of the questions which somebody asked in one of the earlier classes. Sir, what happens to the this similarity transformation using the eigenvectors? So I'm going to do that and then we will discuss that. Which means I am just going to put this guy as the first one and this guy as the second one. So I'm just going to do that. So what will happen that I can write 1 over root 2, 1 I, 1 minus I. I have constructed a matrix which is 2 by 2 matrix, and this matrix is nothing but the column vectors are the eigenvectors of this Hermitian operator. Okay, so I have
So
done that. Yes.
it is required that we have to normalize for the diagonalization.
You will see. You will see. I'll discuss with you. But let's just do this and then we'll go ahead. There is an important item related with the normalization. I want to know P inverse and I want to know P dagger. First, P dagger. What will be P dagger? 1 over 2, 1 over root 2 and
1 minus iota
1 minus iota
1
1 iota.
1
and minus
iota.
iota, sorry.
What about P inverse? How will you get it?
Just interchanging and changing the
So
signs.
1 over determinant of P and then this guy interchange this minus I 1 becomes minus 1 and I becomes minus I. What is determinant of P?
Minus 2 iota.
Okay, so how did you find determinant of minus 2 iota, right?
Yes, sir.
Okay, let me see others. Remember, this is something like this 1 over 2 root 2, 1 over root 2. Just for you to be
Minus
clear,
right.
Yes, sir.
this
With
is
a
this.
with a root
2
2.
iota.
With a root 2.
Yeah, sorry. So maybe can you speak a little bit louder? So this
Minus
is
root
your
2 iota.
minus root
Root
2
2 iota.
But can you just take this? This will become what? Minus I over 2, 1 over root 2 this. Minus I over 2, this will be equal to what?
Minus iota.
Minus
minus
iota.
I.
Minus I. Please see that when you are taking the determinant, do not forget about this root 2 or whenever you are multiplying, please take care of this factor properly. The only reason it happens because we have a habit of first multiplying this and then use only square root 2 as the denominator. But it is not true. Each of this element is getting multiplied by this number. This is the simple scalar multiplication. So generally keep it. And that means, okay, so this becomes what? 1 over minus I minus 1 minus I 1. What will be the result? So minus I divided by minus I. 1 minus 1 divided by minus I. So this number.
Minus iota.
Minus I.
Minus I. Thank you. Minus I divided by minus I again. 1. 1 divided by minus I.
Iota.
Iota. Okay, now compare the two, P inverse with P dagger. P dagger is equal to P inverse. This is a special matrix. What do we call these kind of matrix?
Unitary.
Unitary
Right.
matrix.
Please see that the matrix which we have made out of the eigenvectors of the Hermitian operator, that turns out to be unitary. And now I will give you third task, which okay, I mean a little bit lengthier, but we still want to do that in order to get our result. And what will be that?
But sir, root 2 term is also there in P dagger.
Yes, sir. There is 1 by root
Not
2 in P
equal.
dagger. So it will come out P.
So where does that go? Yeah, this is a good question. Okay.
So root 2 term should also be in P inverse also, nominate.
So where did that go? By the way, in my writing.
So here when you are calculating P inverse.
Right. So you see the catch here
Determinant
that
has
either I
minus
should have
2
written
iota.
root 2
Yes, sir.
everywhere here on the element or otherwise I should have written root 2 here. Thanks for pointing it out now, but it is important that we should not leave any factor and otherwise this thing can happen. Anyway, I will give you a minute to think about it. Please see what we have done and confirm whether you are getting that this matrix of the eigenvectors be unitary or not. Take 1 minute. Checked, not checked? Somebody can confirm?
Checked.
Yes, sir. It is
1 by
using
root
Okay,
two
so we were
factors.
missing this root 2 factor. Thanks for pointing it out. But ultimately, you should get this result that P dagger should be equal to P inverse, which means that this matrix P turns out to be a unitary matrix. And now the final thing which I want you to do, little bit lengthier, P inverse, and then okay, this I got T operator times P, which you can, I mean, it is same as doing this. So remember that we have our linear operator given in the orthonormal basis. I want you to now multiply it from the left and the right hand side, P inverse in P or P dagger or P. Can somebody think of what is going to happen?
We get a diagonal
We will get
matrix.
a diagonal
So
of
let's just see whether we are getting or not. So 1 over 2 of P inverse or P dagger, it is one and the same thing. Why I have written 1 over 2 and not 1 over root 2? Because I have P inverse and P, right? And what was our matrix T? Let's go to the previous page and see it was 0 minus I 0. Just that 0 minus I 0. Okay. And do not know why this guy has not come properly. 0 minus I, and then our original P, 1 iota 1 minus iota. So I want you to multiply this and give me the result.
So it's 1, 0, 0, minus 1.
Okay, 1 0 0 minus 1. You have
Yes.
checked it or you have got the, you know the result?
No, sir, I found it. Calculate.
You found it. Okay, good. You calculated it. Good. Let me see others.
Yes, sir.
Okay, second confirmation. I need one more.
Yes, sir, it's correct.
Yes, sir. Getting same.
It is correct. So let's
Yes,
just see what we have done. We have diagonalized our original matrix. So let me just go back to the question and give the essential aspects out of that question. So basically we took care of all the things which I have done. I told you that we started with one operator whose matrix representation is such that it is a Hermitian matrix or correspond to self-adjoint linear operator. The word self-adjoint is generally used in almost all the quantum mechanics book because as you can understand, we are talking about operators and somehow the word Hermitian gets stuck with the matrices. But other books, of course, use Hermitian also very commonly. So a matrix which correspond to Hermitian one. We found the eigenvalues and the eigenvectors, and we found that this in this particular case we have distinct eigenvalues, and hence the two eigenvectors which we got, they turned out to be orthogonal. Uh, Not only that, if I construct a matrix out of these two eigenvectors, which are the normalized one, then the matrix is such that we have the unitary one. This unitary matrix can be used to diagonalize our self-adjoint operator with, of course, the same one relation which I gave to you earlier. So let me write in a simple manner. And in this case, I have diagonalized it. So diagonalizing a matrix is a special case of change of basis transformation, in which if P is chosen to be the eigenvectors of the Hermitian operator, then the result which you get is basically the diagonal one. And you already know what the diagonal result would be. The diagonal result can only be the eigenvalues of the operator. What were the eigenvalues of the operator? 1 and minus 1. In fact, without even diagonalizing, you know what the result would turn out to be: 1, 0 and 0 minus 1, basically the diagonal result. Had you chosen E2 to be the first vector and E1 to be the second vector, then in that case, what happens?
-1 parallel
Minus 1,
vector
0,
plus
0, plus 1. So in that case, it will still be diagonal, except that the diagonal entries will be interchanged. Nothing else, nothing beyond that. So unitary matrices constructed from the eigenvectors of the self-adjoint linear operators are used to diagonalize a Hermitian matrix. Now, this also answers one very important question. Are these matrices always diagonalizable? Is it always possible to find a basis in which you can write down the operator in the eigenvalue equation form? Or simply put up, is it always are you always able to find a eigenbasis for a linear operator? So what you have answered is you do not know whether you can diagonalize each and every linear operator, but if the linear operator is a self-adjoint linear operator, then surely you are able to diagonalize it. And how you have done it? Using the unitary matrices. So questions up to this point, because I will take you to the next very important concept, which again in terms of a problem, and then we will just discuss it. So we can always diagonalize a Hermitian matrix. How? By finding out the eigenvectors of that. And those eigenvectors will constitute a unitary matrix. That's also a very important thing. It will always constitute a unitary one. Okay, so the next question, which will give you something, another interesting aspect. So let's consider a matrix directly. I am writing a matrix A0, 0, A. Now, I mean, since I haven't said what the A is, but it is on the diagonal side, since they are always real, is it a Hermitian matrix or not? Or in your case, symmetric matrix or not?
It is symmetric.
It is symmetric. Okay, fine. So whatever we are saying about the self-adjoint linear operator, it can represent one of that. Now, if I ask you to find out quickly eigenvalues of this.
A and A.
So A and A.
So lambda turned out to be, will there be two eigenvalues or one eigenvalue?
One. Both are same.
Two
So
eigenvalue.
in
Two
principle,
eigenvalues same.
Degeneracy.
these are two eigenvalues, but they are identical. So this corresponds to which case?
Degenerate.
Degenerate case.
Degenerate case.
Degenerate.
So now
Degeneracy case.
right, in this case, can we build the orthogonal or linearly independent vectors? We have two vectors. Of course, it's a 2 by 2 matrix. That means that any space V2F space will require two vectors. Orthogonal, very good. Linearly independent, sure. I mean, those two vectors can generate or span the whole space, can act as a basis. So can we find the basis for this? In order to do that, let's just find out the eigenvectors. So in this case, there is only lambda is equal to A. So there will be only one relation. What will be that relation? So you will have 0, 0, 0, 0, x, y, 0, 0. What does that mean?
The x and y can
Take any value of
take
x
any
and
value.
y.
It
Any value
means
of
it
They are
like
arbitrary.
both are in.
That means any x and any y, as long as they are real numbers, they basically give you the result. Very good. There is no constraint either on x or y. Wow. Now, can you write down this vector, which is given x and y, in terms of something which is a linear combination of, let's say, linearly independent vectors? Can I write xy, a general xy, in terms of any two vectors? I need two.
Yes, sir. We
zero
can write alpha 1 1 comma 0 plus alpha 2 0 comma 1.
Okay, so if I have to write xy, then I will write x times 1 0. This is what you are, y times 0 1,
Yes, sir.
right? Which means you have found out that even though xy could have taken anything, but you can always write down it as the linear combination of, in this case you have already used orthonormal vectors, right? And these are two orthonormal vectors. That means these two vectors are sufficient to constitute the basis, right?
Yes,
Yes.
sir.
Yes. So that means that even though in this case we have a degenerate vector, we have degeneracy, that means that the two eigenvectors correspond to same eigenvalue. I can still make linear combination of orthonormal vectors. By the way, is this combination unique which you have made for this one, x10 and 01? Is this the only possible orthonormal set in which you can expand it?
No, sir.
No, sir.
No, sir.
So I can actually, it's no longer a unique set. In the earlier cases, you were finding out the unique vectors. In this case, since you are finding out as a linear combination of orthonormal vectors, there can be many such sets. And any such set you can use to, again, I mean, of course, you can always form in rather trivial, because your matrix was already diagonal. So what were we expecting? I mean, we are going to get an identity matrix for this P, which will diagonalize this matrix B. I mean, of course, it diagonalizes, but the problem itself was diagonalized. However, the important aspect, this will happen to any system which will have the degenerate system. There you can always find this xy as the linear combination. So let me just try to generalize the result without actually proving it, that even for the degenerate case, if there is m-fold degeneracy in n-dimensional space or linear vector space where m is less than m, then we can find set of m vectors which, when added to rest of the n minus m vectors, to form a basis. So what have we said? We said that it is immaterial whether we have the degeneracy or the non-degeneracy. The only difference in the case of degeneracy is that we will not get a unique set of orthonormal vectors, but we will set plenty of such orthonormal vectors which can be added to rest of the vectors to still form the basis. So if it is an n-dimensional space and m-fold degeneracy, so m of those vectors have same eigenvalues, then the linear combination, I mean this m, whatever the degeneracy is, you can always write it down or expand in terms of those m orthogonal vectors. And those m orthogonal vectors can be added to rest of the vectors to do this, to still form the basis. So this is very good aspect of the self-adjoint operator. One, eigenvalues are always real. Two, eigenvectors will always form the basis. So these are the two very important things which we have got. And these two important aspects allow you to write down your quantum mechanics, I mean the formulation of the quantum mechanics in a very nice manner. We will ultimately do that. I want to give you, I mean, I want you to just play with this. And what can be the best way to give one more problem or two problems, and then you just try to work it out and let me know whether you understand it or not.
Sir,
Yes.
sir, I had a problem, sir, in the previous page.
Okay. Yes.
Um, Sir, here it is said that we would have m vectors. We can find orthonormal set of m vectors, but sir, if it is one-fold here in the above problem, if it is one-fold degenerate, then
It is a two-fold degeneracy. It's not called
sir,
one-fold. I mean, because one is basically non-degeneracy we used. Yes, go ahead.
yes, sir, then twofold degeneracy, then so there should be m less than equals to n
No, in this case, n is equal to m. Yeah.
so then there should be m less than equals to n folds we
No,
can have.
let's just say, let's just write down. I mean the numbers. Okay, so I should use. Just wait. Just a second. I use screen and then write down the numbers, and then you let me know where I went wrong. 2, 2, 2. So in this case, 2. 2 minus 2 is equal to 0. So what happens that you can add these two vectors to 0 vector to form the basis, right?
Yes, sir.
So it is because you are thinking that it is one-fold degeneracy. No, it is called two-fold degeneracy.
Okay, sir.
Yeah, there is nothing as one-fold degeneracy. In fact, one-fold is always non-degenerate. Yeah, the degeneracy is two-fold degeneracy is when two eigenvectors have the same eigenvalue. One-fold degeneracy means one eigenvector having one eigenvalue. So that of course. So it is just the nomenclature, I guess. Is it fine?
Yes, sir.
Okay. So let me just give you a problem number 1, and then I will give you problem number 2. You will just play with that. But for making problem number 1, I want you guys to little bit think also. So let me give you a transformation. This transformation, by the way, is going to be very important in general. Okay. So I have this very badly drawn Euclidean space XYZ, so your regular one, and I am talking about a transformation about the x-axis in the anti-clock direction by 90 degree. So what am I going to do? I am going to make an operation which is what? So I use this about the x-axis. I am going to rotate by 90 degree. What will happen to y? What will happen to z? So let's say E1 represents this, E2 represents this, E3 represents my X, Y, and Z. So these three vectors correspond to, let's say, my set of orthonormal ones. Now I apply an operation. Operation is what? That I am going to rotate by pi by 2 along the positive x-axis. Now what will happen to E1 first? What will happen to that? So yeah,
Remain
think about it like a
unchanged.
screw.
Remain unchanged.
So this will be
Same, sir. Remain unchanged.
so
It will remain same.
E1. What happens to when I apply this operation on second basis vector, which is E2?
Phase of
It
So
will
what
become
happens to
E3, sir.
this
It will
will
become
become
E3.
E3, and what happens to my Z, which is E3?
becomes minus E2.
Minus E2.
Minus E2.
Minus E2. I can ask you to write down the matrix form, and I am just using the single word R. What will be the size of the matrix? Matrix representation of this operation.
3 by 3.
3 by 3.
3
3
by
by
3.
3. Okay, and can you give me the columns?
Sir, first one is 100,
Okay, which is coming from the first one. Then the second one,
001,
0, 0, 1. Third
0
one.
minus 1 0.
0
0
minus
minus
1
1
0.
0.
0 minus 1.
0 minus 1 0. Okay, so now you have got this kind of a matrix. What I will ask you to do, I will ask you to find out eigenvalues, eigenvectors of this matrix R. Fine. And I will give you another question. So just like the way we found out, please found out and see if you can diagonalize this matrix R. So figure out whether you can diagonalize it or not. And then I give you another one, which is where I am directly giving you a matrix 1 0 1 0 2 0 and again 1 0 1. And I ask you to again do the same problem. Eigenvalues, eigenvectors and diagonalize. You will find in one of the cases there will be degeneracy, in the other case it is purely non-degeneracy. Whenever it is a non-degenerate case, you can find out three vectors which are unique within the phase vector, of course, and those three vectors can be used to diagonalize the matrix. That means the resultant will be the diagonal matrix. And in another case, you will get eigenvalues corresponding to some sort of degeneracy, and you will figure out whether it's a threefold or the twofold degeneracy. And then you will see that in that case, you can still write down that degeneracy in terms of linear combination of orthogonal or orthonormal vectors, and you can still form a basis. So you can still use the eigenvectors to still form the basis. You are not using the eigenvectors uniquely, but you are able to write down those eigenvectors in terms of some sort of a linear combination of orthonormal vectors. Questions here? No, so that in that case, I will just tell you that this as the summary, what we have done to in this class, that we defined a self-adjoint operator. Self-adjoint operators have real eigenvalues, very useful for our physical observables. Self-adjoint operators have the vectors, the eigenvectors, which can form the basis independent of the degeneracy or not, which means that I can always use one of the bases which I call the eigenbasis of that operator, self-adjoint operator, and that can be used to expand rest of the vectors of that vector space. So that way, diagonalization problem, that way the eigenvectors, finding out the eigenvectors and the eigenvalues, those become very useful, because we will see that when we are going to make our final verdict on our quantum mechanics, then all these concepts are the ones which go into the formulation of our quantum mechanics, where we will say that Hermitian operators will represent the physical observables, and the results of the measurement of those physical observables are nothing but the eigenvalues of that operator. So we will use those in our quantum mechanics. Okay, with that I will of course pause unless until you have a question.
Excuse me, sir.
Yes.
Can you explain this conversion again? I lost my connection in between.
Conversion, this guy
No, sir,
x10.
last slide only. That are, yes, sir, this only one.
Okay, okay. Oh, this conversion. I mean, sorry. So let me just do that. Yeah, this guy sometimes becomes zoom, zoom, zoom. I want to zoom up and it is giving me all the zoom down. Wow. So in both the sides, it is zooming up and down. So I will take another page and I will
You can do
explain
undo,
rather than.
I guess.
Yeah, I mean, this is a jog and not exactly the undo thing here. But let me just explain it. I guess it will be clear. So for example, when I am putting r pi by 2, which is on I, your x-axis remains same, right? This is fine. I hope. Is this fine? That when you are applying
Yes,
pi
sir.
by 2 on
Continue.
the, so this basically can be written as what? 1 of E1 plus 0 of E2 plus 0 of E3, where E1, E2, E3 are orthonormal because I took the independent axis, right?
Okay, sir.
And similarly, R of the same acting on E2, which gives what? Y axis becomes your Z axis. So this is this, which is what? 0 of E1 plus 0 of E2 plus 1 of E3, right? And lastly, R of this guy on E3 minus of E2, which is 0 of E1 minus 1 of E2 plus 0 of E3, right? So now this guy becomes your first column 1 0 0. So this is 1 0 0. The next column will be 0 0 1. This is how we write the transformation in the matrix form, right? And then 0 minus 1 0. So 0 minus 1 0. This is the matrix form. Does it make sense?
Yes, sir.
Yeah, this is all. So it is basically writing the matrix representation of the, I mean, the same linear operator, the one which we have been using. Anything else?
No.
Okay. Then I will upload the slides, etc. Okay, fine. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you,
Thank you,
sir.
sir. Guys,
Thank
stop
you,
this.
sir.
Thank
Bye.
you.